Hello everyone, welcome back to my class, and we were in module 5, and in the last lecture we were introduced to interferometer, which relies on division of amplitude, wherein we talked about interference between two reflected rays, and then we studied about the condition of maxima and minima both in reflected arm as well as in transmitted arm. Today we will generalize this concept and we will go to multiple reflections. Yeah. Therefore, today we will talk about thin parallel films, a generalized case, and we will again then move to wedge shaped films. Yeah, we will talk about interference pattern produced by a wedge shaped film also, apart from the usual parallel films. Yeah. Now, just to revive your concept, a layer of material is referred to as thin film for a given wavelength of electromagnetic radiation when its thickness is of the order of that wavelength. Yeah, if the film thickness is of the order of the wavelength, then only we call the film as thin film. Yeah. Apart from this, here we also considers that the light which is falling on the film is coming from a monochromatic source. Yeah. And what does the film do is that it splits the light into different reflected and transmitted light or transmitted and reflected beams. Yeah. Now, since the same light is being splitted or the same light is being transmitted multiple times and reflected multiple times, therefore, all these transmitted and reflected components will have same frequency, but of course, they will all have different amplitudes. Yeah. Now, let us consider that we have an extended source here. Okay. Now, we shifted to extended source from a point monochromatic source. Okay. Now, if the source is extended, then the rays from these extended source will fall at different angles on the interface of the first interface of the thin film. Yeah. The thin film is again here and it has a certain thickness and refractive index is N1. The refractive index of the media above and below the film is N1 and N2 respectively. Yeah. Now, the ray which starts from here will fall here, and the ray which start from this point of this extended source will fall here. Okay. Now, suppose a parallel beam of light is starting from the extended source, which are represented by this red line here. These are the two rays or waves which are parallel and they are falling on this film, the first interface of the film. Therefore, after reflection this ray will go here and then there is a converging lens which will tilt the direction and it will fall at point P2 on the screen. But apart from this, a part of the ray will get transmitted, it will suffer reflection from the lower interface of the film, and here again after transmission it will become parallel to the first reflected ray. Yeah, these two rays would be parallel and then they will again, since they are the parallel rays, it will again converge to P2 point on the screen. Similarly, this ray which is parallel to the first incoming ray, it will also suffer reflection and transmission, and ultimately it will also get converged to point P on the screen. It means the rays which are parallel and they will fall at the same angle at the first interface. What I mean to say is that this angle would be equal to this angle, the theta I would be same here in both the cases. Okay. The rays which are parallel will fall at the same angle of incidence at the first interface of the film, and after reflection all these parallel rays will go to the same point. This is 2D concept in two dimension. Similarly, the rays which are again parallel, but inclined at different angle, this blue line represents the second set of ray. Yeah, this is again a parallel beam of light, but with a different inclination with respect to the first interface of the thin film. They will again suffers through the reflection and transmission, and then they will converge to point P1 here. Okay. It means the angle of incidence decides where all these rays will go. Okay. The rays which are falling at the same angle are getting converged to the fixed point on the screen. Okay. Now, let us go move in a 3-dimensional plane or 3-dimensional space. Yeah. Now, in 3D the source is extended and the film is also a 3D film now. Okay. It has both length and width, and the depth is very small, which is of the order of the wavelength. Now, in that particular case, this common point P1 and P2, they will trace out a circle, and therefore, the fringe pattern which we will see in this particular case where the source is extended, it will be of the form of concentric circles. Yeah, this will be the fringe form. Yeah, the fringes would be in the form of concentric circles. Yeah. Now, there are few points which must be noted before moving ahead. If the lens used to focus the rays has a small aperture, then the interference fringes will appear only a small portion of the film. Yeah, if the lens is very small, the aperture is very small, then only the fringes will will appear only on a very small portion of the film. Okay. For an extended source, light will reach the lens from various directions as shown in the previous figure, and the fringe pattern will spread out over a large area of the film. Yeah. For the point source, there was a small area where the fringes were visible. Now, for extended source, ray will fall on the film from different direction, and then the fringes will also be spreaded. Okay, and therefore, they will appear on a large area of the film. Now, the third point, the angle of incidence theta I are equivalently the angle of transmission theta t, because they are directly related, determined by the position of P will in turn control the phase difference del. Okay. The angle of incidence or the angle of transmission, therefore, will control the phase difference, which is very much obvious. Yeah, because if you changes the angle of incidence, the path difference will change, and therefore, the phase difference will also change, and therefore, they will decide whether at a particular position on the screen whether there is a maximum or minimum. Okay. The fringes appearing at point P1 and P2 in figure are known as fringes of equal inclination. Yeah, which is very much obvious. Why? Because the rays which subtend the same angle with respect to the normal to the point of incidence, they are converging to the same point. Okay. Let us go back to the figure. You see this, the red beam is going to point P2, while the blue ones are going to point P1. The red ones are subtending the same angle, therefore, they are getting converged to the same point which is P2, and similarly for the blue. Okay. And therefore, the fringes which are obtained in this way are called fringes of equal inclination. Okay. The rays which incline by same angle will fall on the same fringe, and therefore, fringes of equal inclination. Okay. Now, this is the setup for the fringe formation. You see, this is the extended source, and from the source the beams are going to this this semi silvered glass plate or semi reflecting glass plate, and this glass plate direct this rays to the thin film, okay, which is this one. Okay, this is the thin film or thin dielectric film, and then the rays suffer multiple reflections here, and then through this lens they are converge to this screen and we see the formation of circular fringes. Okay. The equal inclination fringes that are seen for thick plates, now if the plate is thick, are known as Haidinger fringes. Okay. There is a particular property of these fringes, and what is this property, or what are the prerequisite for the formation of these fringes? For the Haidinger fringes, the angle of incidence must be either equal to or very close to 0, okay, or these fringes must fall on the glass plate almost normally. Okay. And these fringes can be seen in ordinary glass window also, or the glasses which are installed on a storefront. Okay. These are called Haidinger fringes. Okay. Just remember normal incidence and for the thick glass plate. Yeah. Now, apart from these fringes of equal inclination, there is another class of fringes. Okay. And what is this new class of fringes? This new whole class of interference fringes exist where the dominant term is the thickness. Let me reframe it. Now, apart from this fringes of equal inclination, there exists a separate class of fringes which is called fringes of equal thickness. Fringes of equal thickness means this part difference which is given by cap lambda. Here you see that there are terms which depends upon NF and there are terms which depends upon theta t or theta I. If the part difference is angle dependent, then we get fringes of equal inclination. It is also possible that we have a film in which d is changing, d is variable, and in that particular case fringes become d dependent, they become dependent on the thickness of the film. Okay. And therefore, the dominant parameter now becomes NF into d, which is optical path length in a medium of refractive index NF. Okay. And therefore, a whole new class of interference fringes exist for which the optical thickness, which is NFD, is the dominant parameter rather than the angle of incidence or angle of transmission, which is shown here in this equation number 12. Okay. And these fringes are referred to as fringes of equal inclination. Yeah, this is the new type of fringes, fringes of equal inclination. Okay. Thus, we are introduced to two types of fringes. First is fringes of equal thickness, and the second is fringes of equal inclination. Yeah. Now, here we talked about fringes of equal inclination. Okay, there is a mistake. These fringes are referred to as fringes of equal thickness, not inclination. Okay, it is wrongly written because NFD is now the variable and the fringes is now dependent on NFD instead of theta I or theta t. Therefore, such kind of fringes are called fringes of equal thickness. Okay. Therefore, we studied two types of fringes. First is called fringes of equal inclination, which we study in case of parallel film, and the second type of fringes is called fringes of equal thickness, and this type of fringes appears where the thickness varies, and the best example is wedge-shaped film. Okay. Therefore, under this topic we will talk about this type of fringes which are called fringes of equal thickness. Okay. Now, you see that there is a medium of refractive plates of refractive index N1 and N2, and they are inclined at some angle alpha. Yeah, this is angle of inclination is alpha. Then between these two plates there is a film of refractive index NF, okay, whose thickness is increasing as we go away from this point. Okay, if we move in this direction, in plus x direction, then you see that its thickness is increasing. Okay. This film of refractive index Nx, this shape of the film is called wedge shape. Okay. This is the shape of the film. Okay. and this film thickness is increasing as we move away from the point of our line of contact between the two plates, then we see that thickness of the film is increasing slowly and this angle is kept very small. Okay. Now, if we may incident a beam almost normally to the first interface of this wedge-shaped film, then we again get some type of interference pattern due to again multiple reflection and transmission here, both in the transmitted arm and reflected arm we will see a fringe formation. Okay. Now, for normal incidence, okay, the fringe pattern which arises is called Fizeau fringes. Okay. We talked about Hedinger fringes, now this is Fizeau fringes. Hedinger fringes appear in case when the fringes are of equal inclination, but for equal thickness case we have Fizeau fringes. Okay. Now, consider we have a thin wedge and the angle of the wedge is very small, which is represented by alpha here. Then the optical path length difference between the two reflected rays may be approximated by equation number 6, which we covered in last lecture. Now, this equation says that optical path length difference is equal to 2 NFD cos theta t. Okay. NF is the film refractive index, but what is D here? D is the thickness, but thickness is varying as you move away from the line of contact. Okay. Therefore, D is expressed by this relation, D is equal to x into alpha, where alpha is very small angle. Therefore, from this figure you can see that tan alpha is equal to this d by x. Here d is a function of x, of course. Yeah. And when alpha is very small, then we can write alpha is equal to d by x or d is equal to alpha into x. Okay, d, the thickness is now function of x. Yeah. Here x is measured from the line of contact. We assume that the x is 0 there, and as we move away from that line of contact, x increases in positive direction. Now, under this condition, for small values of angle of incidence, the condition for interference maximum will be given by equation number 13. Okay, we are just following the last class lecture. Okay, and here dm is the thickness of the film where mth maxima is observed, and as we know dm is equal to x into alpha. Therefore, we write dm as alpha into xm. xm represent the position of the mth maxima from the line of contact, of course. Yeah, if the maxima is appearing here, then if mth maxima is appearing here, then this is xm and the corresponding thickness is dm. Okay. Now, we have already defined that Nf is equal to lambda naught by lambda f in the last class. Therefore, xm from the equation number 14 can be expressed by this relation, which is equation number 15. Okay. Now, you see that, like, if you plot these things, then you can easily visualize that fringes here would be straight line fringes. Okay. And the fringes switches from dark to bright and bright to dark as we move away from the line of contact, as you increase the thickness of the wedge. If you vary the thickness of the this wedge, the fringes alters. Yeah, it goes from bright to dark and then dark to bright and so on. Yeah, and this is shown here. Okay, but you also see that this position of the fringe, it depends upon the angle alpha also. Okay, the mth position of mth bright fringe, it depends upon alpha, it depends upon nf, it depends upon lambda. Okay. Therefore, if you change alpha or lambda, the position of this bright fringe will change accordingly. Now, from the previous relation, the first two consecutive maxima occur at x, which is given by lambda f by 4 alpha and 3 lambda f by 4 alpha. How? Here if you substitute m is equal to 0, then you get lambda f by 4 alpha. Okay. Second, the next interference maxima will occur when m is equal to 1, and which if you simplify will give you 3 lambda f by 4 alpha. And from these two relation, as we did in Young's double slit experiment, we can calculate the fringe width, okay, the separation between the two consecutive maxima, which is delta x, and if you subtract these two, you will get this relation. This is fringe width, and this is shown here in this figure. You see the separation between two maxima is delta x. Okay. Now, this separation is inversely proportional to alpha, the angle, yeah, and therefore, if you vary alpha, if you increase alpha, the fringe width decreases, and this is what exactly is shown here in this figure. Yeah, here if you go from left to right, alpha is increasing if you go from left to right, and therefore, the fringe width, since fringe width is inversely proportional to alpha, it will decrease, and this is what is exactly happen here. The fringe width is large, here it is has got reduced, and here it is very small relatively. It's a slowly decreasing as alpha is getting increased. As we increase alpha, the thickness of the fringes are reducing, okay, which is very much clear from equation number 16 also. Okay. Now, these all figures are taken from these references. Yeah, I always mention the references here down. Yeah, all these materials are either from optics by E. Hecht and A. R. Ganeshan, or from optics by Ghatak. Yeah, all this figure, all these contents are from there. Now, notice that the difference in the film thickness between adjacent maxima is equal to lambda f by 2. Yeah. The d, if we move from one maxima to another maxima, the d varies by only lambda f by 2. Okay. Now, once you can calculate d from equation number 13. Yeah. Now, since the beam reflected from the lower surface traverses the film twice, yeah, because when you fall light here, when you incident light here, then it goes into the film and then it get reflected and then comes out. It means the reflected light travels twice the length of the film. Therefore, the adjacent maxima differ in optical path length by lambda f, okay, and the film thickness at various maxima is given by this relation. Okay. And similarly, you can calculate the expression for various minima. Okay. And this is all for fringes formed in wedge shaped film. Okay. And this is all for today, and we will meet in the next lecture and then read further. We will talk about the next topic in this module 5, which are Newton's ring, very important topic. Yeah. And I end my lecture with this, and thank you all for listening me. See you in next class.